Welcome to our journey through the cosmos. Today, we're going to explore the very origins of everything around us, starting with the universe, the Big Bang Theory, and the incredible forces that shape stellar evolution. Before we dive into the deep end, let's establish some basic vocabulary. You will often hear the word cosmos, which is simply another term for the universe. Anything cosmic relates to this vast space. For example, cosmic rays are highly energetic particles zipping through space at nearly the speed of light. They are actually quite dangerous, as direct exposure can cause genetic mutations. Moving on, we have cosmology, which is the scientific study of the universe on a grand scale, looking at its overall properties. When we talk about cosmological events, we are referring to the origin and development of the universe itself. And of course, astronomy is the broader study of specific celestial objects like stars and planets, as well as phenomena that occur outside our Earth's atmosphere. So, what exactly is the universe? Simply put, it is all existing matter and space. It is so incomprehensibly large that it defies human imagination. It includes physical things, from the tiniest subatomic particles like electrons to massive galactic superclusters. But it also includes non-physical components that govern how things interact, such as light, gravity, and the very fabric of space itself. To give you a sense of scale, scientists estimate that the observable universe contains about 100 billion galaxies, and within each of those galaxies, there is an average of 100 billion stars. Our own home, the Milky Way galaxy, is actually quite robust, believed to possess anywhere from 100 billion to 400 billion stars. The numbers are truly staggering. How did all of this begin? The prevailing scientific model is the Big Bang Theory. It states that about 13.8 billion years ago, all of space, matter, and energy were compressed into a single, infinitely dense and hot point called a singularity. From that imaginable state, the universe rapidly expanded outward in all directions, and it has been expanding ever since. Let us trace the timeline right after the Big Bang. In the tiniest fraction of a second, the cosmos underwent a super-fast inflation, ballooning from the size of an atom to the size of a grapefruit. Shortly after, it was a seething hot soup of fundamental particles like quarks and electrons. As it cooled slightly, quarks clumped together to form protons and neutrons. Even at 3 minutes old, it was still too hot for atoms to form, and the dense fog of particles trapped all light. It took 300,000 years for the universe to cool enough for electrons to bind with protons and neutrons, forming the first atoms, mostly hydrogen and helium. With the fog lifted, light could finally travel freely through space. By 1 billion years, gravity pulled these primordial gases together to form the first stars and galaxies. Billions of years later, as massive early stars died, they forged heavier elements, scattering them into space to eventually form planets and new stars. But how will it all end? One hypothesis is the Big Crunch. This theory suggests that at some point, the expansion of the universe will halt. Gravity will take over, causing the universe to collapse back in on itself. It would become incredibly dense and hot once again, eventually crushing everything back into a single point of infinite density, much like the singularity that started it all. However, current observations point to a different fate. We see that the universe's expansion is actually accelerating, a concept described by Hubble's law. Because matter is spreading out faster and faster, the universe will likely get increasingly colder. What is driving this acceleration? Scientists attribute it to dark energy, a mysterious force that permeates all of space. The universe entered this dark energy-dominated era about 5 billion years ago. You might wonder how we know all this. The Big Bang Theory is supported by three major pillars of observational evidence: the cosmological redshift of galaxies, the discovery of the cosmic microwave background radiation, and the detection of gravitational waves. Let's look at each of these closely. First is the Doppler shift, specifically redshift. When an object in space moves away from us, the light waves it emits get stretched out, shifting toward the red end of the spectrum. Conversely, if it moves closer, the waves compress, shifting toward the blue end. American astronomer Edwin Hubble observed that distant galaxies are overwhelmingly redshifted, meaning they are moving away from us. This was the first major proof of an expanding universe. The second piece of evidence is the cosmic microwave background, or CMB. If you look at space with an optical telescope, it looks dark, but a sensitive radio telescope detects a faint, uniform glow in the microwave spectrum coming from everywhere. This is relic radiation, the literal afterglow of the Big Bang. It is the oldest light in the universe, and its discovery was a massive landmark in proving the Big Bang Theory. The third major piece of evidence involves gravitational waves. Predicted by Albert Einstein in 1916 as part of his general theory of relativity, these are literal ripples in the fabric of spacetime. When incredibly massive objects, like black holes or neutron stars, accelerate or collide, they distort space around them. These distortions radiate outward at the speed of light, carrying information about their violent origins. These waves are generated by violent events, but by the time they travel across the cosmos to reach Earth, they are billions of times smaller than an atom. Incredibly, in 2015, the LIGO facility in the USA physically sensed these microscopic distortions. The waves they detected were generated by two massive black holes colliding nearly 1.3 billion light-years away. To understand these waves, we must look at Einstein's work. In 1905, his special relativity showed that space and time are not separate, but interwoven into a single continuum called spacetime. 10 years later, his general relativity proposed that massive objects actually warp and distort this spacetime fabric. What we feel as gravity is simply objects moving along the curves of this distorted spacetime. A fascinating consequence of general relativity is gravitational lensing. Because massive objects warp spacetime, even light has to follow that curved path. When light from a distant galaxy passes near a massive object like a black hole, the light bends. The massive object acts like a giant magnifying glass or lens, allowing us to see things that are hidden directly behind it. Gravitational waves are not just a neat proof of Einstein's theories. They are incredibly useful tools. They act like cosmic sirens that help us measure the universe's expansion rate, known as the Hubble constant. By observing a collision, the flash of light tells us the velocity, while the gravitational waves give us a precise distance. Together, they provide a highly accurate calculation of how fast the universe is expanding. Before we move on, let's clarify a few extreme cosmic concepts. A singularity is a point where gravity is so intense that our normal laws of physics break down entirely. A wormhole, predicted shortly after Einstein's theory, is a theoretical shortcut through curved spacetime. And finally, the Chandrasekhar limit, named after the brilliant Indian astrophysicist, defines the exact mass point at which a dying star will inevitably collapse into a black hole. Understanding these extreme limits sets the perfect stage for exploring how massive structures form. Let's dive right into the concept of a galaxy. A galaxy is essentially a massive system containing millions or even billions of stars, along with vast amounts of gas and dust. All of this material is bound together by gravitational attraction, making galaxies the major building blocks of our universe. When astronomers observe the billions of galaxies out there, they broadly classify them into two basic types: regular galaxies and irregular galaxies. Irregular galaxies make up about 1/10 of all galaxies and typically contain very old stars. Zooming in on regular galaxies, we see two main structural shapes: spiral and elliptical. Spiral galaxies have a flat, disk-like shape with young stars forming in their gas-rich arms. Elliptical galaxies, on the other hand, are generally smaller, dimmer, and filled with older stars, as they lack the gas needed to form new ones. Now, when scientists measure how fast spiral galaxies rotate, they notice a major discrepancy. When scientists measure how fast spiral galaxies rotate, they notice a major discrepancy. The outer arms rotate much too fast to be held together solely by the gravity of the visible matter. This implies there must be extra unseen mass, what we call dark matter. It turns out that everything we can see makes up less than 5% of the universe. Dark matter and dark energy make up the other 95.1%. We call it dark matter because it does not interact with light or any part of the electromagnetic spectrum. We only know it is there because of its gravitational pull. Bringing things closer to home, let's look at our own galaxy, the Milky Way. It is a spiral galaxy shaped like a flat disk with a thick central bulge, spanning up to 200,000 light-years across. You often hear the term light year when discussing space, but it is crucial to remember that a light year is a measure of distance, not time. It is simply the distance that light, traveling at 300,000 kilometers per second, covers in one Earth year. The Milky Way is incredibly vast, containing between 100 and 400 billion stars. Our solar system sits in the Orion Arm, orbiting a supermassive black hole at the galactic center. Stars are not eternal. They are born, they live, and they die. This process, known as stellar evolution, follows a specific sequence of stages depending on the star's initial mass. A star's life begins in a nebula, where gas and dust collapse under gravity to form a protostar. At this stage, the core isn't hot enough for nuclear fusion, but as gravity continues to compress it, the temperature eventually reaches the millions of degrees needed to fuse hydrogen into helium. Once nuclear fusion ignites, the star becomes a main sequence star. About 90% of all stars, including our Sun, are in this phase. The most common type of main sequence stars are red dwarfs, which are small, cool, and faint. As a star like our Sun exhausts the hydrogen fuel in its core, it enters the red giant phase. The core compresses and heats up enough to fuse helium into carbon, while the outer layers expand massively, cooling down in the process. To understand what happens next, we need to look at the delicate balance inside a star. Gravity constantly pulls matter inward, while the energy from fusion pushes outward. When fusion stops, gravity wins, crushing the core into an incredibly dense state known as degenerate matter. For an average-sized star, the red giant phase ends with the star gently shedding its outer layers into space, forming a beautiful planetary nebula. What remains is a white dwarf, a tiny, fiercely hot, and incredibly dense core. If a white dwarf is in a binary system, orbiting close to another star, it can siphon off hydrogen from its companion. A small buildup causes a bright surface explosion called a nova. But if too much mass accumulates, it triggers a runaway thermonuclear explosion, a Type 1 supernova that destroys the star completely. Type 1a supernovae are incredibly important to astronomers. Because they all explode with nearly the exact same maximum brightness, scientists use them as cosmic beacons to measure vast distances and calculate the expansion rate of the universe. Now let's look at much larger stars. When a massive star runs out of fuel, its iron core collapses instantly, resulting in a spectacular Type II supernova. The extreme energy of this explosion creates heavy elements, like gold and uranium, scattering them across the cosmos to form new stars and planets. After a massive star goes supernova, the core that remains is subjected to unimaginable gravitational pressure. Protons and electrons are crushed together to form a neutron star, an object so dense that 3 times the mass of our sun is packed into a sphere just 20 kilometers wide. If the collapsing core is massive enough, not even the pressure of neutrons can stop the crush of gravity. It collapses infinitely into a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. Moving from the extreme physics of dying stars, let's look up at the night sky. For millennia, humans have grouped stars into recognizable patterns called constellations, such as Orion the Hunter or Ursa Major. Constellations are incredibly useful for navigating the night sky. For example, you can use the 3 stars of Orion's belt to point directly to Sirius, the brightest star. Similarly, the pole star, Polaris, sits directly above Earth's northern axis, making it appear stationary while all other stars revolve around it. Finally, consider how our position on Earth changes our view. If you observe stars rising perfectly perpendicular to the horizon, you are standing on the equator. This is because the stars revolve parallel to the celestial equator. That wraps up our detailed look at galaxies, the life cycle of stars, and the mechanics of the night sky.